So here I am at the University of Leiden on a beautiful day in actually it's becoming late June. It's amazing. Summer is upon us. I'm with an astronomer who is well known in her field, the study of protoplanetary disks, Nienke van der Merel. Did I pronounce your first name correct?
Yes, perfect.
Okay. Uh, we were just in your office discussing protoplanetary disks, your 2013 discovery, actually with using ALMA. You were one of the first astronomers to benefit from the use of ALMA. First, tell us what ALMA is and how it is enlightening our view of protoplanetary disks.
Yeah, so ALMA is not a single telescope, but an array of 66 telescopes that are all working together to create beautiful images of dust and gas in the universe. And so ALMA is a radio telescope, so it means it observes at very long wavelengths that you cannot see with your own eye. And what is so unique about ALMA is that it allows us to zoom in to incredible detail to the disks around young stars, which you can imagine like little pancakes made of gas and dust with a tiny hole in the middle where the star is. We want to study that gas and dust because that is the formation material out of which eventually the planets are created. And with ALMA, we can look at these disks and make images really at the scale of the inner solar system.
And this is all in the infrared.
In the far infrared and submillimeter.
Far infrared and submillimeter, correct? Okay. So you told me that you were interested in the big picture, not just one system, but you're looking in collecting enough data to be able to say what really is going on, how protoplanetary disks form after stars form, the onset of planet formation, how we go from a giant molecular cloud down to the collapse of the cloud to a protostellar disk and then the protoplanetary disks. And there are a lot of questions that remain. You said you'll probably still have a job for the next 30 years because there's still many questions to be answered. But in 2013, you made a discovery. Tell us about that still stands today.
Yeah, so what I discovered in 2013 with some of the first ALMA observations was the presence or the existence of a dust trap in a protoplanetary disk. And so a dust trap is a location where millimeter grains, or pebbles, are concentrated in one part of the disk and where they can continue to grow all the way to planetesimals and planets. And the reason that this was such an important discovery is that it had been suggested for a long time that these dust traps must exist in disks, but it had never been observed before. And so the reason that they're so important has to do with a problem that we call radial drift. So in a smooth protoplanetary disk of gas and dust, we know that the gas and the tiny dust grains, the tiny little sandy grains, as they are rotating through the disk, move at sub-Keplerian speed.
And what do you mean by sub-Keplerian speeds?
That means that they move 0.1% slower than what the laws of Kepler would tell us. And this is caused by the fact that that the gas and the temperature decrease when you go outwards from the sun, from the star to larger radii. So because of this decrease in temperature and density, you essentially get a decrease in pressure. And that change in pressure exerts an additional force onto the gas and the small grains, making them move slower. However, in the same system, you also expect some pebbles to be present. And these pebbles are there because the smallest dust grains collide with each other and stick together, forming these larger grains, these larger pebbles. However, these large pebbles, they don't they don't feel this pressure gradient anymore. They don't experience this additional force. So what they want to do is move on Keplerian orbits, right? They're not hindered by this additional force. But so they're trying to move fast, but they're surrounded by all this gas and tiny dust grains that are moving slower. So they feel this as if there was a headwind, like there's a lot of wind that they're trying to go against. Well, the solution of nature in such a case, if you experience a headwind while you're rotating, is that you lose angular momentum and then move inwards towards, in this case, the star. And in the 70s, it was calculated that this inward movement that we call radial drift was really, really efficient. Essentially, as soon as you form or create such a pebble, it moves inwards in only 100 years. And that means that there is not enough time, as soon as you have a pebble, to meet other pebbles and continue to grow to planetesimal sizes. So you need something that stops the pebbles from drifting inwards. And that phenomenon that was proposed to stop it was a dust trap.
A dust trap.
Yeah, and a dust trap, or also called a pressure bump.
And these dust traps exist in systems which already have a planet that's formed, but in a gap that the planet has carved out in the dust, in the gas and dust in the protoplanetary disk. Is that correct?
Correct. So as soon as you form a first planet, somehow, we don't know yet how that first planet gets formed, it will carve a gap along its orbit, and then at the outer edge of that gap, you naturally get a maximum in the density, a bump in the gas density or in the pressure. And that means that now the pebbles that come from the outer disk, they still move inwards, they still drift inwards, but then at that pressure maximum location, they get trapped, and that's why we then call it a dust trap. So this hypothesis already existed for quite a long time, that something was present in the disk that could hold the pebbles, but we didn't really know if that was truly the case. And then in 2013, with some of the first ALMA data, I observed one of these dust traps directly.
In IRS 48.
In the system called IRS 48.
Right.
Yeah. Of course, this whole idea creates a major chicken and egg problem, because if you need a planet to create dust traps, and then dust traps are necessary to form planetesimals and planets, then where did that first planet come from?
So how did you get the first planet? That's the chicken to form to carve the lane that could form a dust trap, which would have a higher density of these pebbles that could then build planetesimals, which are the building blocks of planets.
Exactly.
So,
and that is still a problem until today.
And in our own system, we have a gas giant Jupiter. And let's say, for argument's sake, that Jupiter formed first, and it formed by a mode that's, it's been theorized or hypothesized that there's a means of in an early disk of disk fragmentation, which early on in exoplanet studies, there was a fellow named Alan Voss, a planetary scientist, a very well-known planetary scientist at the Carnegie Institution of Washington, who proposed disk fragmentation as a means for perhaps even forming Jupiter. But today we don't think Jupiter formed by disk fragmentation, do we? Or do we know?
Honestly, we don't know for sure. There's a lot of ideas that have been around for a long time that are now being put to debate again.
So tell us what disk fragmentation means in a protoplanetary sense, and why that could solve, in our instance, the chicken and egg problem.
Right. So disk fragmentation is a process where part of the disk is essentially the entire disk is very massive, and then part of the disk gets slightly more massive, and maybe gets disturbed by turbulence or infall that triggers the sudden gravitational collapse in one location of the disk. And in that collapse, all the material suddenly moves towards the center or towards the point of the highest density, creating a clump, and that quickly starts to eat up all the surrounding material, forming a massive planet.
Like Jupiter, a gas giant.
Like Jupiter, or even more massive.
And so that would solve the chicken and egg problem for how you could get a dust trap to form terrestrial mass planets. That would solve the situation in our own system. But let's say that we learned that Jupiter did not form by disk fragmentation, or you take a system like the TRAPPIST system, which has gotten so much attention, which is 7 terrestrial mass planets circling a red dwarf star. And to my knowledge, there's no evidence for a gas giant in that system. Is that correct?
Correct.
So that would mean that in systems that did not have a gas giant, you have no explanation for how you form a dust trap, correct?
Correct, yeah.
Which means the chicken and egg system would continue to persist.
Yeah. In those systems, you would need another way to concentrate the dust at the right location.
And indeed, this is a big problem because, as you yourself have said, higher mass stars like GK spectral types are probably more likely to form gas giants than lower mass stars like red dwarfs. And the deal with red dwarfs is they're the most ubiquitous form of star in the cosmos, no question. 60 to 70% of all stars are red dwarfs, correct?
Yeah.
So your chicken and egg question still persists.
Absolutely. So I'm not out of a job anytime soon.
And when do you think this problem can be solved, or how it would be solved?
I don't know yet. It's there's a lot of telescopes going to be online in the coming decades that will teach us more about the composition of exoplanets, which may tell us a bit of how they formed. With ALMA, we continue to improve the array, getting higher sensitivity, getting higher resolution, so even more detail. The NGVLA is another up-and-coming telescope, which is just like ALMA, an array, but observing at even longer wavelengths, where we can trace even larger dust grains. So that may help us to understand where most of the planet formation goes.
That's in New Mexico.
It's in New Mexico and the southern parts of the United States.
So final question, and I'm sure this is something you think about every day. From your work these past years, and from the work that ALMA is doing, how rare do you think our own solar system is? I mean, are we an anomaly at this point, or do you know?
It is impossible to say right now. We don't have the data to say for certain whether we are an anomaly or not.
Thank you so much, Nienke, for your time today, for being so generous with your time.
No problem.
Very interesting subject, and we look forward, hopefully, that you'll have a new paper that maybe puts us on the road to solving this chicken and egg problem soon. Thank you.
Thank you.